As we continue our study in how to apply Newton's laws of motion, we will, in this series, be taking a look at some dissipative forces, namely friction and drag. In this video, we'll take a look at friction, and broadly speaking, we can break friction into two major regimes, and then there's one minor case that we won't really get into too much. One regime you can break it into is static friction. This is where the two surfaces in question are stationary with respect to each other. The other major category is kinetic friction, which is where the two surfaces are moving with respect to each other. And it's important to note here, when I say, for instance, that static friction means that the two surfaces are stationary with respect to each other, they could both be moving as long as they're moving at the same rate. So as long as so say an example we'll be taking a look at in a bit is, say you have a crate in the back of a pickup truck. If the crate isn't sliding around, that's static friction. Even though both the pickup truck and the crate are moving, they are stationary with respect to each other. Kinetic friction is when the two surfaces are sliding against each other or moving with respect to each other. There is a third model of friction that sometimes gets brought out. I'm not going to make a big deal of it here, but some books mention it, and I often think it causes more consternation than it's worth. There's rolling friction, which this has specifically to do with wheels. Usually it's really small, so actually I'll just say that. So it's usually small. Usually you can get away with not making a big deal about it. The only time you might care is, say, if you're designing cars or something like that, then the rolling friction of tires matters. But I don't think that's really worth getting into too much here. I'll have more to say about it later after we explore static and kinetic friction. But mostly not going to be making that big of a deal about it. All right, so let's go and take a look at static friction. So in static friction, the object is stationary with respect to the surface. So for instance, let's just say you just plain have a crate that's just sitting on the ground, and that's it. What would the force of static friction be? Well, 0. It doesn't need to be anything. In fact, if it were something other than 0, it would be moving because there wasn't any force to oppose it. Now, say if you had somebody start to push on the crate, but it was a heavy crate, the surfaces were rough, you couldn't get the crate to budge and it stayed put, then the force of friction, static friction, would be non-zero. And we'll get into how that works in a second. But now let's think about, let's say we have a crate that is stationary on a ramp. Well, here we know that there's a force of gravity trying to make the crate go down the ramp. So this means that there does need to be a force of static friction to keep it from moving. And in general, to figure out how big the force of static friction is, you have to know one of two things. You either, and this is always the safest thing to do, is solve Newton's second law of motion for it. The other possibility is sometimes you'll be given coded information in the problem. Usually a phrase something like just about to slide. or what is the maximum I can push, phrases like that. And the reason is that there is a limit to how hard static friction can push. We've seen our force of static friction could be as low as 0. And we know from our practical experience, if you push on that stubborn box hard enough, it will budge. So there is a maximum force that static friction can be. And if what static friction needs to be to keep something from moving is bigger than that, well, it gives up and starts sliding, and then we switch over into the regime of kinetic friction. Now, this is an empirical model, and there are plenty of derivations that have been done in different scenarios. And then paradoxically, it always seems to keep coming up with the same result. So this is one of those models that works way better than it has any right to. But this is just a model. We don't have a law of friction here. This is just a model. So in the static regime, this maximum force of static friction turns out to depend on two things. One of the things it depends on is the strength of the normal force acting on the object. And the other thing is a parameter that characterizes the overall roughness of the two surfaces and the intermolecular forces between the two surfaces and whatever else you can think of. This gets called the coefficient of static friction. Yeah, I can draw T, static friction. In case you're wondering what this weird letter is here, this is a lowercase Greek letter mu. If you remember this sort of paper that we all learned to write on in like second grade, the way you draw mu is you start below the bottom of the line, go up, and then make kind of an M-like shape. That would be how you would make a Greek letter mu. Okay. So these coefficients can be looked up in tables. Typical values for these, for the coefficient of static friction, depends on what the material, again, like I said, depends on what the materials are, but just to give you some sort of sense of things, most of the time you'll see values of mu(s) ranging between about 0 and 1, but it turns out that with like really weird things, it can run to about as high as 20 in the case of like specialty racing tire compounds and stuff like that. But one of my rules of thumb is that tires are just plain weird. They're made up of all sorts of crazy compounds, and I'm told that even on rare occasion, if necessary for the performance, they sometimes even put rubber in them. They're weird beasts. They behave in weird ways, and how friction even works when it's a tire is different. But this is your typical range. So most of the time, if it isn't tires involved, if you have a coefficient of static friction that's bigger than 1 after you solve for it, you should probably be a little worried. And definitely, if you start getting much bigger than 20, those are like really sticky drag racing tires. Okay. And it's important to note that this is not a vector equation. This is a scalar equation. That's why I didn't draw any little arrowheads over it. This is because the direction for friction is parallel to the surface. Whereas, of course, the normal force is perpendicular to the surface. And the direction is whichever way is required to keep object from stationary with respect to the surface. Okay. So, like I say, in general, when you are figuring out what if static friction is what's involved, your first instinct should be to solve Newton's second law of motion for it, unless you are given coded information that you just happen to be at the maximum value for static friction, in which case you can use the coefficient. You can then say that static friction happens to be equal to the coefficient of static friction times the normal force. But most of the time you'll have to solve Newton's second law for it. So let's do that example I was mentioning a little earlier. Let's go and take a look at that crate in the back of a pickup truck. Ooh, well, that's weird. There we go. There's our pickup truck. And then let's go stick our crate in here. Let's say our crate has a mass of 100 kilograms. And let's say the coefficient of static friction between the crate and the truck is 0.7. Let's say at the moment the truck is picking up speed and it is accelerating to the right at 2 meters per second squared. So there are two things we need to know. The first thing is does the box slip? And if not, what does Fs max, or sorry, what does Fs equal? Okay. So we're going to have to take a two-prong approach here. First thing you're going to have to do is just assume that the box doesn't slip and solve for what the force of static friction would be required to keep it from slipping. You'll then have to calculate Fs max and compare the two to see if the box actually slips or not. And that's about the only way I know how to do it, is you just kind of have to trial and error it a bit. So, all right, let's do our force identification diagram here. And we can look at this and we can see, all right, we're going through the surface of the pickup truck bed. There'll be a normal force. And there has to be a force of static friction as well. One, we're asking for what it is, but also two, if there were no force of static friction being exerted. By Newton's first law of motion, the crate would be moving forward at a constant speed, while the pickup truck would pick up speed underneath it, and so it would slide off. Since we're assuming that it's not sliding off, or well, we're trying to figure out whether it is or not, so I have to at least temporarily assume it's not sliding off, then that means there needs to be a force of static friction to keep it from slipping. And then that's it for the contact forces. So our long-range force is the usual suspect, gravity. All right, so let's go ahead and draw a free body diagram for our crate. So we'll go ahead and put in the normal force. We know that that's going to point straight up. And we know that gravity is going to point straight down. Now we know that the force of static friction is going to be parallel to the surface that exerts it. So that means it's going to be either straight right or straight left. So I'm going to ask you to pause here for a moment and ask yourself, is the force of static friction on the crate to the right or to the left? Okay, So it turns out that the force of static friction here has to be to the right. And why is that? It's because we know that the crate is accelerating to the right. And the normal and friction, normal and gravity are going to cancel because they're in the x direction, in the y direction, and those are the only two forces in y. And the crate is neither flying off or crashing through the truck. The only other force left, because we did our force identification diagram, is friction. And so the net force has to point to the right. Normal and gravity are canceling. So it's got to be the case that friction is the force pointing to the right. Oddly enough. Again, it might make a little more sense if you don't like thinking of it that way. Another way to think about it is to ask yourself, which way would it try to slip relative to the surface? So again, going back to what we were saying before, when we figured out that there was a force of static friction, by Newton's first law of motion, the crate would want to go forward at a constant speed, but in the problem, the truck is picking up speed going forward. So that means that the crate is going to want, even though the crate is moving forward, it would eventually be not going forward as fast as the truck, which means that relative to the truck bed surface, the crate would be moving backwards against the truck bed surface. So we would need friction to push it forward to keep that slipping from happening. Either way you want to think about is fine. So either think about what is the direction of the proposed slipping, and remember that static friction needs to oppose that. Or if you prefer, just plain draw the free body diagrams, draw in the acceleration, and figure out which way static friction just plain has to point. Now, there are some cases where the situation can get pathological enough that you just plain have to guess. And if after you solve for static friction you get a negative magnitude, that means that you guessed incorrectly. So, but most of the time you can figure it out. But there are sometimes pathological situations where you have to guess. So it's not the end of the world if you have to do that. All right, well, let's go ahead and take a look at Newton's laws of motion on this. So first off, we'll just start F net equals ma. So we'll go ahead and add up all of our forces as vectors. So it'll be n plus fg plus fs equals ma. Now what we'll do is we'll go ahead and take the x and the y components of this. So in x, so this will become nx plus fgx plus fsx equals max. Well, the acceleration is entirely along x, so we can just write ma. The normal force is 0 in the x, and gravity is 0 in the x, because they're both going purely in y. And the force of static friction is again purely in x, and since it's to the right, it's positive. Okay, so we get that the force of static friction will be equal to ma. And the mass we said was 100 kilograms, and the acceleration is 2 meters per second squared, gives us 200 newtons. So we've kind of had to solve this backwards. Like I said, we have to first assume that it doesn't slip. So we've solved for Fs. So if it doesn't slip, we found it. And if it does slip, then this was important to calculate to figure out if it does slip so it wasn't wasted effort. Now to figure out if the box slips, we're going to have to go back to our model of friction. In our model of friction, we said that Fs max is equal to mu static times the normal force. So this means that we need to solve for the normal force, And we can do that by looking at the y component of our equation of motion. So we'll just put y's on everything here. So this will be ny plus fgy plus fsy equals may. All right, so here the normal force is acting entirely in plus y, so we can just write n. Gravity is acting entirely in negative y, so we write minus fg. The force of static friction, remember, was acting entirely in the plus x, none of it in the y, so we can write 0 for the y component. The acceleration was purely to the right, so we can write 0 for that. So what we get here is that the normal force is equal to the force of gravity, and by our model of gravity, that's equal to mg. So putting that back into our expression for Fs max, we get that Fs max be equal to mu s times mg. Now again, be careful here. Don't just write mg's or mg cosine thetas right away. You always have to solve for the normal force. You can have situations like, say, I could change this up by, say, having straps tied onto the box in the back of the truck. Those straps would be exerting a tension force down on the crate, and that would serve to increase the normal force, which would increase Fs max. In fact, this is part of why you would actually put straps on an object that you are carrying. Okay, so anyway, we can put in the numbers here. So our coefficient of static friction was 0.7, 100 kilograms, and 9.8 newtons per kilogram for our gravitational field strength. This gets us 686 newtons. So the big deal here with that is that our force of static friction we found was 200 newtons. That's less than 686 newtons. So we can conclude that the box, in fact, does not slip, and that the force of static friction on it is indeed 200 newtons. So that's how you attack something like that. Okay, let's do one more example of this, an example where you're given the coded information about the object being just about to slide. And this is a famous problem called the angle of repose. And if there happens to be an MCAT in your future, odds are really good that this is going to be one of the standalone questions. So let's say you have a ramp that is tilted at 37 degrees and you have a box. Yeah, you're right, I didn't tell you what the mass was. But we have a box sitting on here. And what we're told is if we tilt that ramp just even the slightest bit more, it'll start to move. So this is where we would say that this is the highest angle where it won't slide, or we can say that if we tilt it any higher, it just begins to slide. Now in this problem here, what I want to find is what is the coefficient of static friction between the surfaces. Okay, let's go ahead and do that one. So in this case, we can do our force identification diagram again, and it will give us the same forces we had before. We'll go through the surface and know that we have a normal force and a force of static friction. And then our long-range force is gravity again. All right, let's draw a free body diagram. So you got the normal force up and gravity, or perpendicular to the ramp, and gravity straight down. And we know that the crate wants to slide down. So since it wants to slide down, we're going to need the force of static friction to point against the surface in order to cancel everything out. All right, so we'll go ahead and follow the first law of inclined planes here, as I like to call it, which is always choose a tilted coordinate system. So this is plus x, that's plus y. By the second law of inclined planes, this angle is that angle. So this angle is also 37 degrees. So with that, let's go ahead and start expressing Newton's second law for this situation. Now this is an equilibrium situation. In fact, it's static equilibrium because it's not moving at all. So we can start by saying F net equals ma. And here the acceleration is the zero vector. So this is going to tell me that the normal force plus gravity plus the force of static friction equals 0. All right, now there are two ways that you can do this, but let's just go by taking components because I think that will be the more straightforward. I might throw in a second way just as fun bonus content. We'll see. So this piece here will be FGY. That piece there will be FGX, just so it got marked out. All right, so let's go ahead and take the x component of this. So this will be nx plus fgx plus fsx. And the x component of 0 is, well, 0. Now the x component of the normal force is also 0. Fgx will be Fg times the sine of theta, because Fgx is the opposite and Fg is the hypotenuse. Minus force of static friction, points all the way back, equals 0. Okay. So we can start by putting in our models, and we'll have to pause and go to the land of y for just a second here. So mg sine theta minus our model of friction is mu s times the normal force. So that's as far as we can take it until we solve for the normal force. To get the normal force, we'll have to go to the land of y. So taking the y components of this vector sum, there'll be ny plus fgy plus fsy equals 0. Static friction is entirely in x, so that goes away. The normal force is entirely in y, so we can just write n. And gravity is in the negative direction, and this is the adjacent, so it would be cosine. So Fg cosine theta. So that gives us that the normal force is equal to Fg cosine theta, and Fg is mg. All right, so now we can go and put that into, put that into there. So that's going to give me mg sine theta minus mu s mg cosine theta equals 0. All right, so we're solving for mu s here. And notice I never gave you the mass. If I didn't give you the mass, then that means it jolly well better cancel or we're in trouble. But that often happens in problems with gravity because of the equivalence of inertial and gravitational mass. So here we'll have mu s mg cosine theta equals mg sine theta. Hey, I can divide both sides by m and g, and they cancel out. Divide both sides by cosine theta, I get mu s equals sine theta over cosine theta equals the tangent of theta. So that would be the tangent of 37 degrees, and 37 degrees is the interior of a 3, 4, 5 right triangle. So you can use that to figure out that the tangent of 37 is roughly 0.75. Don't bust my chops if it's off by 1/100th. All right. This gets called the angle of repose for interesting historic reasons. Before the development of things like steel girders and stuff like that, if you wanted to build a bigger building, you had to build a wider building. So for instance, if you look at the Great Pyramids, they are very, very wide at the base. And the reason for this is that the building material, this case sandstone, if I remember correctly, will, if you build it too steep, the grains of material within the rock will start to slide against each other, and as a result, the pyramid will crumble. You can find evidence of this because in the very earliest pyramids found, the angles were much steeper. And then once they started getting too big, there's evidence that they were starting to collapse. And in fact, you can even find one pyramid where it started going up steep and then angled in less steep in order to keep it from collapsing. And then going forward, they were all pretty much hanging out at exactly the same angle. And this angle is just a little bit shallower than what you get if you just let sand fall through, fall through a little hole and see what angle the cone takes up. And that turns out that angle, the angle of repose, is because that's the coefficient of static friction between the grains of sand, and the building material they're using wasn't too different than sand, so that was an excellent approximation. Okay, now I did promise potential extra bonus content here, and I think I'll go ahead and present it, but you don't have to if you don't like it. So when we look at the equation of motion here, we said that the normal force plus gravity plus the force of static friction equals 0. So this means that the vector sum of these adds up to 0. So the normal force did this. The force of gravity did that. This angle is 37 degrees. And the force of static friction does that, and that angle is 90 degrees. So you can go ahead and just do the trig directly off of this if you prefer. We can say that Fs, the ratio of Fs to n, has to be the tangent of the angle, in this case 37 degrees, because this is the opposite and that's the adjacent. And the force of static friction is mu s n. So we can go ahead and cancel the normal forces and get straight off that the coefficient of static friction is the tangent of theta. This sort of trick only works in equilibrium situations, because that's where doing the vector sum will go to 0. And it only really works cleanly if you got 3 forces. So if you like it, great. And if you don't, by all means, just go back to land of X, land of Y. It will always work. But I just thought I'd show that as some fun bonus content there. All right, so in the next video, we'll go ahead and pick up with kinetic and rolling friction. See you in a bit.